I'm Dr. T. Welcome to my office. Today I'd like to talk about setting up labs in order to account for random error. Now, when I'm talking about random error, I'm talking about the random variations in your measurements. What I'm not talking about are mistakes where you just mess something up. If you mess something up and you're like, oh, this was wrong, and you can articulate why this is wrong, then you just get rid of it and redo it. That's not error, that's mistake. Also, I'm not talking about things like inhomogeneity of samples. So if you've got, say, a train car load full of chemicals, and the top, middle, and bottom have a slightly different blend of chemicals because you can't mix a whole train car load. There's ways to deal with that I'm not going to cover. That's its own separate category. Now, what I'm looking at is every time you do a measurement, every time you do an experiment, we are mortal, we are not perfect, we're not divine, and you're going to get slight variations. Sometimes they'll be a little bit too big, sometimes a little bit too small. So when we do this, the way we account for this is we try and let the random error cancel itself out. So we'll do the experiment, but we'll do it several times. Ideally, start to finish, completely repeating the experiment, what we call replication. Alternatively, sometimes during the experiment, there's the key phases of it, and those will run 2, 3, 4, 10 copies of. All at once. So instead of a massive replication, we replicate within the experiment. And so once we do this, what we're going to get is a series of numbers. Now, in a perfect world, they'd all be exactly the same, but we live in the real world, so they won't be. So when we look at these numbers, we're going to get a bit of a spread. And so the question is, well, how do we deal with these numbers? One approach, assuming we took a reasonable number of replications. Usually when we start talking replications, 3 is the hard minimum. Larger number is better, ideally even into the hundreds for something that's particularly important, because that really lets the random error average itself out. But usually we're talking 3 to 10 kind of range. One thing we can do is known as a t-test. In that case, we're looking for outliers that are statistically different than the rest, and that implies that a mistake had taken place. Typically, this is only going to flag things that are really far outliers, and it's not something you want to be too aggressive with, because what you don't want to remove are things that are on the edge but not mistakes, because it could really be telling you that the center of your error isn't really in the center of your numbers, kind of thing. Once again, for that error to really truly all cancel out, you really need to do dozens, hundreds of samples and replications. So you don't want to be throwing them away too easily. Okay, so you've got your data set. You may have removed a couple of outliers, a couple of numbers that are really, really too high or really, really too low by looking at a t-test and doing statistics on that. Now, the next question you have is, okay, how am I going to turn this into something useful? And the way we're going to do that is we're going to find the average. And this is the exact same average you're used to. Add them up, divide by the total you got. And this provides an average number. And this is really where the error has been canceled out, because you've added all your numbers up, you've divided them out. Those that were a little too high have met ones that are a little too low, and the highness and the lowness have canceled each other out. If you had enough samples and they were of enough quality, boom, you now have your good and true answer. But there's a couple of things we can still look at to really understand what's going on. For starters, a spread in your population or a spread in your answers, depending on what's going on, could be random errors during your experimentation, or it could be, if these are separate individual samples, could actually be a spread or a variation in the actual population that you're looking at. So, if I'm measuring the height of people, the difference between people is probably not going to be my ability to measure them. It's probably just simply that some people are taller than other people. So this is a valuable piece of information. Also, how wide my spread is, what I call precision, is a good description of, well, how well I've done in measuring. If I have a nice tight spread, then that says, hey, I've got a high precision, it's done well, this looks good. If I've got a broad spread, then I've got some issues with precision. My precision is low. Whatever I'm using to measure them is having problems. And maybe I need better tools to measure them with if that spread is large enough that it could cause me problems. Now, to look at that spread, we usually use a mathematical equation known as the standard deviation. In this case, it's looking at the spread and then looking how this would fit in a Gaussian curve. And that's one of those kind of classic bell curves. And the standard deviation is partway along one side of a bell curve. And the idea here is, hey, if I've got a nice small standard deviation, that's pretty good. If I've got something that's a different sample that's very far away from my mean, that they're probably different. If it's fairly close, ooh, they're similar. And I do fairly close by, is it within one standard deviation, two standard deviations, etc. Now, typically, we won't leave standard deviations as is. Those are going to be in the same units as the average. Instead, we will do them as a percentage. So we take the standard deviation and divide it by the average. And in that case, that gives us a relative standard deviation, which is usually a slightly more useful description of the precision. So it depends on what we want to use. But with those techniques, you can usually get kind of the basics. If things get funky, you got more complicated samples, especially if you're ever dealing with humans, you're going to go for a much more advanced statistics than what I've described here. This is kind of the basics for the chemicals. Chemicals are nice as they tend to be fairly well behaved. You've got quadrillions, of individual atoms, just an inconceivable number of actual molecules that are going on. So the chemistry is going to tend to average itself out anyways. So you're really looking at your measurement issues in that case, in which case a simple averaging usually works reasonably well, as long as you've got reasonably good precision to start with and you've done a reasonably decent number of samples. But once you start getting really complicated scenarios where what you're measuring is your error plus differences in your population, you're looking at much more advanced statistics that are beyond my scope. So with that said, hey, happy experimenting and see you next time.